Welcome, everybody. This morning, the first talk is on Tomasz Kania about complex CK spaces of topological stable rank 1. Up to you, Thomas.
Thank you very much. Let me start with an apology that I can't be with you, but I definitely failed with our procurement office and was not really, it was not really ready for me to arrange this trip. And congratulations to Alberto for his outstanding thesis defense. So I'm truly sorry that I can't be with you, but I'm very happy that I can deliver this talk here. So because the workshop has CFK in the name, I decided actually to put it maybe slightly artificially in the title. And as you can probably guess, or not, I will explain it in a second, the title is a bit a red herring, in the sense that, well, it doesn't say anything interesting because topological stable rank is a notion from, let's say, Banach algebra theory that I will explain. But for spaces of continuous functions, it reduces to, in the complex case, it reduces to the projective or to the covering dimension of the underlying space K to be at most 1, so 0 and 1. So the title doesn't really say anything what I'm going to talk about. So let me give you some prehistory and some motivation of the results I'm going to discuss. By the way, this is mostly about a joint paper with my PhD student Natalia Myślani from Krakow. So suppose we have the following situation. We would like to study openness in a very basic sense, like a real analysis 1. So let's say that a map is open whenever it maps open sets to open sets. And of course, by Banach's theorem, bounded linear surjections are open. But interestingly, it was not really known up to mid-70s whether this carries over to bilinear map. And Paul Cohen, the one known for the solution of the for his contribution to the continuum hypothesis, and also a renowned person in harmonic analysis, constructed a bilinear map on O1 that is surjective, but it is not open. And actually, the construction was quite involved. Later, 1 year later, actually, Horowitz observed that this fails in finite dimensions, so you can have maps on finite dimensional spaces. Here, his example was going from C3 to C4. But the standard multiplication of real numbers or complex numbers, say, is open, and it's a basic calculus exercise. Because actually we have explicit dependence of the delta. It's epsilon squared over 4, so no problem at all. But we will return to this particular delta later. So let's say write this once again, but I will be caring about also the uniform version of openness. So if we start with openness in this epsilon delta setting, well, then this is nothing but mapping, well, finding balls inside the image of a ball. So, well, of course, you do it in a uniform. Well, you say that a map is open in a uniform way whenever you can swap the quantifiers in the usual real analysis 1 type way. So nothing too fancy. And this name is slightly unfortunate, but it was suggested in some papers, so I decided not to change it. That the map is weakly open if images of open sets have non-empty interior. Okay, so let us have some examples, I guess. One of the best-known examples of nonlinear open map is the exponentiation for continuous functions. It is open, but actually it is a nice exercise to show that it is not open uniformly. But when you take the multiplication, let's say in Rn with the supremum norm, then the proof that you have for the real numbers, well, carries over in a very simple way. because you do it coordinate-wise. So you have uniform openness with the same delta. And actually, in finite dimensions, openness and uniform openness of bilinear maps are equivalent by compactness. But occasionally, we're going to care about the deltas. So here, let us work with this particular norm. Okay, and that's an interesting thing. Namely, Fremlin noticed that all this business in developed by Cohen and Horowitz was maybe overly convoluted, because it is actually a simple application of the intermediate value theorem that multiplication in the real space of the real space of continuous functions is not open to the identity map, and the reason is well, I leave it to you. Take any your favorite number less than half and use the intermediate value theorem. So the question is, one of the questions you could ask, well, what can you say about openness of multiplication in the space of continuous functions? But there is one more example, finite dimensional. Actually, you can show that matrix multiplication is not open. It's not open, so you can have it in dimension 4, right? 2 by 2 matrices. But it is weakly open in the sense that open sets have, well, images of open sets have non-empty interior. Okay, so let me talk about multiplication in function spaces. And here is a result in the real case that actually completely describes openness in terms of dimension. So for a compact space, when you are in the real setting, what you could do, well, you could say is that in dimension 0, well, you have uniform openness. So that when your space is totally disconnected, actually the same epsilon squared over 4 works as a delta. In dimension 1, it is weakly open, but not open. And in dimension greater than 1, it is not. So even though it is specific to continuous functions in the real setting, I think there is a lesson that we can learn from this. And I'll explain this in a second when we pass to a more general setting of Banach algebras and transferring this question to the question of openness of multiplication in a Banach algebra setting. Okay, so there are lots of results concerning function spaces. I think I haven't quite updated that. Numerous combinations of authors, and actually this list is incomplete. Over the last 2 years, I think more results have been provided. Well, results in the sense that either something was proved or refuted in terms of what is open and what is not. Actually this became quite active. Okay, so my interest in this question started when somebody asked me, well, when actually Marek Walcerczak asked me, well, is the Cauchy product of absolutely convergent series open or uniformly open? And well, my way of thinking is to go abstract, trying to do something, use some sledgehammers and return. And indeed, you can follow this by generalizing or by translating this to the language of Banach algebras. Well, this is a fine Banach algebra because, and actually, not only is it a Banach algebra, but it's a Banach algebra of a very special type. You take a semigroup, and it is a convolution semigroup. So what is convolution in this general setting? Well, we take you take two, let's say, functions, yes, or tuples indexed by the elements of the semigroup, and well, you take all possible expressions of the of a given element of a semigroup into products, take the coefficients, and this is what you put on the S coordinate. So for groups, or in particular for Z, it translates to the familiar formula for convolution because you can take the inverse. For a general semigroup, of course, you can't, therefore you need to consider products. Okay, so this is a well-studied class of Banach algebras. So maybe there is something related to this and involving the structure of the semigroup itself. And when S is a monoid, so when S has a unit, this is unital, but actually the converse need not, well, it doesn't hold. So you can make L1 of S unital even though the semigroup doesn't have a unit. But we're not going to look into such examples today. But what is important, or what was natural to me, is that semigroups of semigroup homomorphisms naturally lift to, or canonically lift to, homomorphisms of the convolution algebras. Simply, for an element, what you do, you take the corresponding unit vector basis whose index is the value of a homomorphism of a given point, and to this, by the maximality of the norm in L1, extends to first of all, this is a well-defined mapping of, let's say, algebraic version of convolution algebra, which is nothing but the group ring, and then by maximality of the L1 norm, it extends continuously. So that's very nice. That's a very nice feature of L1 VES. So, well, you can ask for which semigroups the convolution is open in L1 VES. Or more generally, well, for which Banach algebras multiplication is open or uniformly open. Okay, so the idea actually is to notice that there is a link, at least one way, between openness and having lots of invertible elements. And what we could do in the non-commutative setting, we could use the following characterization of finiteness due to Mark Riefel, saying that for a unital Banach algebra, well, we have the following are equivalent. The group of invertible elements is dense in A. The right invertible elements are dense, and the left invertible elements are dense, and in either case they are the same. So it's like for matrices, yes? So when a matrix is left invertible, then it is invertible. So such a phenomenon holds in general. So as long as one-sidedly invertible elements are dense, well, they are actually invertible. And also a fact that you'll find on page 4 of every Banach algebra textbook is that when you have a unital Banach algebra and you take the topological boundary of the invertible elements, then they are topological zero divisors. So that in particular we have that the infimum of the, let's say, products with all, let's say, norm 1 elements is 0 in both ways. So you can actually state it like this. Okay, so if we know this, then let us observe that actually in the Cauchy product setting, well, this infimum is at least 1. So this is quite easy exercise. For instance, you could look at your favorite unit vector basis that is not invertible, and actually they are not invertible. Unit vector basis element. So when you convolve, you simply shift, but because of the properties of the L1 norm, you don't change the norm. You simply add zeros to your sequence, so the norm doesn't change. In particular, it doesn't go to 0. So for that reason, well, we can conclude that there has to be something more. I mean, since we have this, well, simply invertible elements are not dense in L1 of the additive semigroup of natural numbers. And it is a super simple observation that we have in my first paper on the topic with Szymon Draga, that multiplication is open as points where at least one of them is invertible. So invertibility gives you a way of of accessing openness, simply, well, you can take any epsilon and you set the delta to be epsilon over 2 times the norm of the inverse. And, well, what you can do, you can express any element from the ball slightly artificially as the product of x and its inverse, because it's 1, and itself, so that you can factorize. So you can write that x inverse times z minus y, well, is at most epsilon half. In that way, you've proved that the product xy and the ball around xy with delta given like this is contained in the product of balls, which proves openness at least for points where one of the items is invertible. So there is at least one link with invertibility, but also it kind of goes the other way around to an extent that when multiplication is open, then the group of invertibles is dense in the algebra. And this is also completely elementary, as long as you're familiar with this result of refill that I mentioned, but at least in the commutative case, it is super elementary, where you take a function that is not invertible, in particular, it is not a right invertible, well, a function that is not in the closure of the invertibles, so it is not in the closure of, say, right invertibles. So for some epsilon, you'll find a ball that is disjoint. Therefore, if you take f naught, it will not be open for f and 0. So that's this. Therefore, there is a link between openness and density of the invertible groups. So I'm not really going to explain the notion of topological stable rank beyond 1. For us, I think 1 is the upper limit of interest, and algebras whose invertibles are dense are exactly algebras that have topological stable rank 1. So instead of explaining this, I will use it as a kind of short description of this fact that in this or that algebra, invertibles are dense. Okay, so here what really happened is that in the Cauchy product setting, well, when you take E1, it is simply not in the closure of invertibles. So convolution, for that very reason, is not open. I mean, the Cauchy product is not open for that very reason. But here, the point is that it is not, because you have this shift, one-sided shift. But in particular, when you change the setting to L1 of Z, then this argument will not work at all. So the question is, what happens for general groups? And before we, let's say, comment on that, well, let us note some simple permanence properties of weak openness, or uniform openness. Well, that they pass to quotients by closed ideals, and the deltas don't really change; they can only improve. And are preserved by isomorphisms, but of course isomorphisms, can twist the deltas, but still. And why keeping those constants is important, because when you want to perform some operations, such as taking the L infinity direct products, then this equi-uniformity will produce for you this this delta in the, for instance, L infinity product of Banach algebras. But when we combine this observation that you can pass to L infinity product, as long as, let's say, the multiplications are equi-uniformly open, and that this passes to quotients by closed ideals, it means that, of course, it passes to ultra products And actually, this is a very handy tool for disproving uniform openness. And in a paper with Schumann, we delivered a very convoluted proof of the fact that L1 of Z, that the convolution in L1 of Z is not uniformly open, and it was quite specific actually to Z. And in this recent preprint, actually we strengthened them by a lot, and the argument is simplified by a lot, even though it still uses ultra powers. That we have the following. So suppose you have a group of unbounded exponent, which means that the supremum of the orders, the orders are not uniformly bounded, the orders of all elements. In particular, if you have an element of infinite order, like in Z, then you have it. Then convolution is not uniformly open, and the reason is is interesting because we have a link with there is a link between the Banach algebra ultra power of L1 of G and L1 of the algebraic ultra power of the group. So there are certain quotients that you can construct to quotient one and to another, and actually conclude that it's not really possible for a group of unbounded exponents. But what are a group of bounded exponents? So groups of bounded, abelian groups of bounded exponents, by Prufer's theorem, they are simply, well, you take your favorite cyclic group and you take some infinite amplification. So you take the direct sum of however many copies you like, and then you are free to add some finitely many other cyclic groups, and that's it. So essentially, from the point of view of this theory and reductions that you could make, the only case that is not covered is when you have an infinite direct sum of any number of copies of your favorite cyclic group. Then we don't know. But actually, we don't know whether L1 of Z has open convolution. And this is a quite critical case of an algebra that motivates our further considerations. So this is related to a notion of differential subalgebras as introduced by Blackadder and Kunz. So suppose, but before we introduce differential subalgebras, let me comment on this. So suppose we have a Banach algebra homomorphism that is injective, and we say that A admits a norm-controlled inversion. Well, if you can't control the norm of invertible elements in the following way, well, it is simply a function of the norm of A and of the norm of the inverse in algebra B. So in our setting, we are going actually to use it mostly in the case where B is the space of continuous functions and the maximal ideal space of algebra. So I will be the Gelfand transform, at least in the case where it is injective. Yes, so semi-simplicity will be needed. So and this is a quite interesting phenomenon, but in general it is difficult to check. But again, it is not very difficult exercise to show that when you consider the algebra of Lipschitz functions on the unit interval, then it has this norm-controlled inversion in continuous functions on the unit interval. So you take the formal inclusion, the inclusion, yeah, and you have it. And actually, what is interesting is this result of Nikolsky in his long memoir about the so-called invisible spectrum. So he was investigating this Wiener-Peat phenomenon in general groups. So if your group is infinite, then actually L1 of G fails to have norm-controlled inversion in this Gelfand algebra in the space of continuous functions on the Pontryagin dual. And note that when you substitute Z here, then the Pontryagin dual is of course the circle, the torus, which is one-dimensional. So in dimension one, everything is nice. I mean, so we understand the topological stable rank of one-dimensional spaces, and in the complex space it is even better because invertibles are dense, and we are happy. But still, this thing is missing. So, but actually, in our considerations, we need a slightly stronger notion, the notion of a differential subalgebra. So a differential subalgebra is an algebra with a norm and this continuous embedding, so that you have a kind of a Lipschitz, Leibniz-like estimate for the product, and again, this alludes to the fact that when you take, let's say, C1 functions in continuous functions, you'll have it. Also by Rademacher or something, you will have it in the space of Lipschitz functions, and many algebras, many natural function algebras appear to be differential in the space of continuous functions on the maximal ideal space. But this notion actually implies norm-controlled inversion. Therefore, L1 of G fail the norm-controlled inversion. So this is, yeah. Okay, so the result that we have, that is on the positive side, is the following. Well, quite a lot of assumptions, but when you look into the proof, I think all of them are well justified, because in general it is very difficult to provide positive general criteria for openness. If you look in the proofs in the literature, then well, what people do, they take some particular function algebra and they work in the particular setting, like in the algebra of BV functions. There are papers where they prove that multiplication is open, but it is quite specific to the situation of to things that you can do in BV. So even though the hypothesis list is quite long, it is, I think, nearly optimal. So suppose you have the following. So you have a unital symmetric dual Banach star algebra. So we are going to use complex, actually we do require complex scalars, because as you saw in the result by Komisarski, or maybe you will see in a moment, that there is a great difference between real and complex scalars. So let us work in a star algebra setting where we can mimic certain arguments for complex numbers. So symmetry, okay, in that setting we just want to, the two notions of positivity, one concerning the spectrum and the containment of a spectrum in the positive half-axis, and this algebraic positivity to coincide. And also we want XA to sit as a differential subalgebra of the space of continuous functions of some space. It doesn't have to be the maximal ideal space, but some zero-dimensional space. And now we have this slightly artificial maybe notion of having densely many points common with X. I'll explain in a second. Then you can prove that, well, that multiplication is open at points such that the sum of the moduli is invertible in the algebra. So, well, you have the star algebra setting in order to define the modulus. Actually, you can take the squares of the moduli. is invertible. So if your algebra has this property that every pair of elements is approximable by elements of this form in such a way that you can guarantee that, let's say, you take two elements, and if you can find two other elements, A prime, B prime, that have the same product and they are arbitrarily close, then you can prove openness. But it is in general very difficult to verify whether you can approximate. So what I mean by this, that there is a compatibility of let's say between point evaluations and, let's say, and functionals. Yes, so in the and characters in your algebra. So we say that A shares with X densely many points whenever you will find a dense set of points in the space is continuous, well, in X, in this compact space, so that when you pull back the evaluation functionals, then they are continuous. Well, then they are weak stack continuous because we assume that we have a dual Banach algebra. Okay, so this applies to BV, to reflexive. I mean this, that we have this automatic or almost, but we have this possibility of approximation by elements with this property that the squares of moduli, the sum of the squares of the moduli is invertible. So in particular in BV, you have open multiplication in, let's say, reflexive spaces with coordinate-wise multiplication and so on. But in general, it's the hardest part to verify whether you have such a possibility of approximation. And actually, the final result I'm going to talk about is a complete characterization of openness in the complex case for CK spaces. Yes, so I wanted really to make it in line with the theme of the workshop. So here it is. So suppose you have a complex space, and we know in the complex case what is the topological stable rank in terms of the covering dimension. So as I said in the beginning, it is at most, so the topological dimension, the topological stable rank is 1 whenever X has dimension 0 or 1, and it is not 1 if the covering dimension is at least 2. But it means that when the covering dimension is at least 2, then invertibles in C of X are not dense. Therefore, you can't have open multiplication. So the question remains, what happens in dimension 0 and 1? In dimension 0, essentially, Komisarski's proof carries over. But actually, there is even an easier proof once you realize that what a zero-dimensional space is. A certain projective limit argument can give you this in 1 second. So for dimension 0, no problem. But for dimension 1, actually, it was quite problematic. So the proof is divided into, the proof of open, and which, by the way, turns out to be uniformly open, multiplication in C of X for X one-dimensional. So it originates with some ideas of Behrens, who was considering this for the unit interval. And then the idea is to extend it to let's say, all graphs. Topological realizations of graphs, finite graphs, because every compact metric space of dimension 1 is an inverse limit of such things. And inverse limit corresponds to a direct limit of algebras. And when you have this equi-uniformity of the deltas, yes, of multiplications, then actually you can pass to a direct limit. So that's why not only we need uniform openness for all graphs, but actually we need equi-uniform openness for all topological graphs. and actually you have it. So once you have it for graphs, you have for all compact matrix spaces of dimension 1, and then you can take you can consider another direct limit argument that every compact space of dimension 1 is an inverse limit of compact metric spaces of dimension at most 1. So this again carries over to every compact space, not necessarily metrizable, so that you can prove that for in dimensions 0 and 1, open multiplication is equivalent to uniformly open multiplication, and that's it. Okay, so I'm about to finish. So some problems. This is my favorite problem, and I have absolutely no clue now what is the answer, whether it is open or not. So I think on Mondays, Wednesdays, and Fridays, I believe it is open. On the remaining days, I believe it is not. And in general, I would be interested in this question. So suppose you have an abelian groups of unbounded exponent. Maybe there you can find a G with open convolution. So that passing to, let's say, passing to direct limits of cyclic groups is an example. Or you can take just your favorite abelian group. In general, we do not, this is maybe maybe strange, but we do not have an example of an infinite dimensional Banach algebra that is non-commutative and has uniformly and has open multiplication. So even though a priori this problem does not seem to be related to commutativity, well, in the non-commutative setting, usually it is not too difficult to show that you don't have open multiplication, but this is again case by case. So whether it is general statement or coincidence, I can't tell. So let me leave you with those open problems, and thank you very much for your time.
¿Ahora funciona? Questions or remarks? Comments? Okay, then let's start the speaker again.
Thank you very much.
Thank you, Thomas. Thank you very much.
Thank you, Jesus.
Good. So welcome again. Our next speaker is Antonio Martínez Abejón, who is going to lie us a lot about the subspace structure of bigger one and the strong property B.
Thank you very much. Congratulations to Alberto for his PhD, also for his advisors. And first of all, I must say that Niels told me that my abstract contains many lies. So actually, it has many sick misprints, and I will show with this first slide. So I'm going to sketch a positive answer to the two following problems. So the first problem says, is it true that for every infinite dimensional closed subspace X of L1, there is a decomposition of L1 into a direct sum of two factors, Y1, Y2, both of them with infinite dimensional intersection with the subspace X? And further, can those factors be taken isomorphically to L1? So henceforth, my notation LP represents the typical big LP on the unit interval, Aurelian subsets, and the typical Lebesgue measure. So the origin of the first question stems in operator theory. So Dixmier and others found that any non-closed dense range operator defined on a Hilbert space is the sum of two non-closed dense ranges, both with null intersection. So later, Theos, Ostrovsky, and Shevchik asked if the same property is also true for Banach spaces, for which Banach spaces actually. So they found a very simple reformulation of the same question, which is called the V property. This property is free of operators. It's quite much easier. So a Banach space X has the property V if for every infinite dimensional closed subspace is there a decomposition of X into two direct summands such that the intersection of Y with each factor is infinite dimensional. So for a Banach space to have property V, it's necessary the subspaces have a good properties of complementation. So the first examples provided by them are the subprojective spaces, which include all big P with P greater than 2, P different than infinite, as I tell you later, and also spaces within conditional basis, which includes all LP with P greater than 1. And spaces without property V, of course, the hereditarily indecomposable Gowel-Mollet space, and any other space containing that Gowel-Mollet space isomorphically, like the continuous functions on the unit interval L infinity and such. So the first question in the opening of my talk can be reformulated as follows. Does L1 have the V property? A question posed by Cross and co-authors. For the next question, Odell and Popov introduce the notion of a strong property V, a strengthening on property V, of course. So, a Banach space X is said to have a strong property V if every infinite dimensional closed subspace has a good splitting in X. That is, there exists a decomposition of X into two summands such that summand factors better, such that every factor has infinite dimensional intersection with Y and both factors are isomorphic to X. So remember those words, anytime I say Y has a good splitting means exactly that. So the motivation for this is that, well, Godefroy and Evia spoke about that yesterday, is the subspace complementation problem in big L1. The only fact I will need in this talk is to know that big L1 is primary, which means that at least one of the factors is isomorphic to big L1. Well, another important fact about the definition you have in first place in the slide is that if you have a subspace Y with a good splitting, then any image of Y by an automorphism on X has also a good splitting. That's trivial because the automorphism become the factors X1 and X2 and other factors which split space X. So obviously, a Banach space with a strong property V must be isomorphic to its square. So the James space, which is projective, so has property V, can't have the strong property V. So, also the central term of this this talk is big L1. It's better if I start with some easy examples of spaces with property V. Of course, those spaces must have better properties for complementation than the case of the plane property V. So the first examples are spaces with subsymmetric bases, like the little LP with P smaller than infinity. Also, strongly subprojective spaces isomorphic to its square. That includes all big P with P greater or equal than 2. But even the big P with P greater than 1 has the strong property B. And finally, the answer to the second question is that L1 also has the strong property B. So, probably some of you don't know the notion of strong subprojectivity. This is as follows. X is subprojective if every subspace has a complemented subspace in X. If the complement is isomorphic to X, then the space X is said strongly subprojective. Until now, it's not known if subprojectivity implies a strong subprojectivity. This is an open question. So, let me give a proof for the case of the subsymmetric basis. This is very, very easy. Take a Banach space X with a subsymmetric basis, Xi with basis constant K, and now take an infinite dimensional subspace. So, you know that Y contains a basic subsequence equivalent to a block subsequence of the subsymmetric basis. And moreover, those elements in the basic sequence Yi are very close in norm, can be taken very close in norm, that's the trick, to those blocks taken in the subsymmetric basis. So, what we do is the following. We need to produce first a good splitting for the sequence Vi. Later I will produce a good splitting for the sequence Yi. We really need that. So, for the sequence Vi, take the block of elements in the subsymmetric basis that make the element Vi. I'll paint them in red. Go for the second element V2, take the corresponding block in the subsymmetric basis, paint them in blue, and so on. For the third element, we take the third block, we paint them in red, and so on and so on. So, the first factor we need is the space, the red space X1, which is the closest span of the red vectors in the subsymmetric basis. And the other factor, X2, the blue subspace X2, is the closest span of the blue vectors in the subsymmetric basis. Since the basis is subsymmetric, both subspaces are isomorphic to X, and they are complemented, and its sum is exactly the Banach space X. Obviously, the red vectors V are contained in the red subspace, the blue vectors V are in the blue subspace, so we have a good splitting for the sequence Vi. So, in order to produce a good splitting for the sequence Yi, what I'm gonna get is an isomorphism, an automorphism on X that maps the corresponding vector Vi on the vector Yi. So, as I commented before, the good splitting of the sequence Vi induces a good splitting in the sequence Yi by means of that automorphism. So, the way to produce that automorphism is just, okay, an argument of a compact perturbation. Consider the subspace V that is generated by the elements Vi. Take the corresponding coordinate functionals of those elements Vi in its dual and take Banach extensions of those functionals. Then, okay, yeah. You can define this compact operator Kx of this form. So, this operator maps every element Vi to the difference Yi minus Vi. Moreover, since this norm is very small, like this, you can compute that this operator is well defined, is continuous, and its norm is smaller than 1. So next step is to take the perturbation of the identity operator by this compact operator K. That's what you have here. So this perturbation maps every element Vi on Yi, and since K has norm smaller than 1, then the identity operator plus K is an automorphism. And then we induce the corresponding with the splitting for the sequence Yi. It's very simple. The next case is for strongly subprojective spaces isomorphic to its square. Actually, next case, LP with P greater than 1 takes parts of a V and the case of the subsymmetric basis. So since this is already published, I don't want to bore you with technical stuff. Let me go directly to case C. So in this case, LP doesn't have a subsymmetric basis, but we take the hard basis. Now we take any infinite dimensional subspace of big LP, and we are going to do exactly the same than in the case of the subsymmetric basis. Exactly the same. So we take a basic sequence of the subspace B, we take an equivalent block subsequence of the hard basis such that the difference between the vector Vi and Yi is as small as 1 places. So for the sake of this talk, let us assume that the blocks Yi are exactly equal to the corresponding vector Vi. So I skip any perturbation argument, which is almost foregone. So after this assumption, we proceed as in the case of the subsymmetric basis. We make red blocks, blue blocks, and then the first block contains, is spanned by the red hard functions. The second space is spanned by the blue hard functions, but now is when the difference starts. The hard basis is not subsymmetric, but Gamlen proved that we face to a dichotomy which solves everything. First case, both subspaces are isomorphic to big LP. In that case, x1 and x2 are a good splitting for the sequence of the vectors Vi, and the proof is over. Or the first factor is isomorphic to big LP, and the second factor is isomorphic to little LP. In the second case, the second factor has a subsymmetric basis. So we can apply the first case, the case of subsymmetric basis, to produce a good splitting of x2 for the even vectors Vi. This good splitting is made with the subspaces W1, W2, both isomorphic to little LP, and then every factor has infinite dimensional intersection with the subspace spanned by the even vectors of Vi. Then what we have to do next is to split the first factor into a direct sum of two factors isomorphic to big LP, which is trivial because x1 is isomorphic to big LP. And then we reorganize the factors of LP. We can see that LP is the direct sum of W1 plus C1, W2 plus C2. So we take this first factor, this second factor. Each of those factors is the direct sum of CY plus WY. So isomorphic to LP, big LP plus little LP, and this is isomorphic to big LP. So since those even vectors V have infinite vectors in each of the factors W, then this intersection is infinite for the factors wi plus cy. And the proof is over. Well, it's over. In case the blocks vi are not equal to yi, what we have to do is to construct again an isomorphism, like in the case of the subsymmetric basis, and the proof is over. And now we are going on the space L1, which is quite harder. It's quite harder because it contains many infinite dimensional reflexive subspaces, and none of them is complemented in L1 because of the Danforth-Pettis property. So, in order to prove that big L1 has the strong property B, take an infinite dimensional subspace of big L1, and we are facing to a dichotomy again. Either X contains a copy of little L1, in which case is known that X contains a complemented copy of little L1 in big L1. Since L1 is primary, in this case, X1 is this complemented copy isomorphic to little L1, but L1 is primary, so X2 is isomorphic to big L1, and then we decompose X1 in two copies of little L1, X2 and two copies of big L1. We proceed as in the case of LP with P greater than 1, and the proof is over again. So because, well, we have here good complementations, it's okay. But the other possibility is that X is a reflexive subspace. So I told you X is not complemented, and of course can't contain any complemented subspace. In this case, I need to proceed with two steps. First step, what happens if X contains a sequence of independent random variables with zero mean? Or just, if you prefer, identically distributed with zero mean, it's okay. And next, the general case. First, the case D21 is a restricted case. So for this case, now I need to make a generalization. I don't have here, as you see, the unit interval. I need to work with a probability measure without atoms. I will tell you later why I do this generalization. Any case, I work with a separable L1 free of atoms, so this is isomorphic to big L1. So, assume Fn is a sequence of independent random variables with zero mean. We take the subsigma algebra generated by the odd functions and the sigma algebra sigma e generated by the even functions f. The corresponding big L1 spaces are both isomorphic to big L1 since we have no atoms here. That's quite easy. In any case, there are more arguments to show that both factors are equivalent to big L1. One of those arguments appeared yesterday in some talk. But well, let me keep going. Well, consider the projection Q, which is defined as the expectation conditional to the subsigma algebra sigma 0. And also the projection P, which is the conditional expectation with respect to the sigma algebra sigma E. Both are norm-1 projections. And by independence, you can see, that's very easy, that the projection Q maps every odd function on itself, which means that the subsequence of odd functions are contained in the range of Q. The range of Q is, as I told you before, is isomorphic to big L1, and for the even functions, by independence, Q maps each of those functions to the expectation of the function multiplied by the constant function 1. Since those functions have zero mean, this expectation is null, so the even functions are contained in the kernel of Q. The same happens with P, but reversing the role even sequence by odd sequence as such. So, RQ, the range of Q is isomorphic to bigger 1, so the only thing we need to prove that the range of Q and the kernel of Q is a good splitting for the sequence Fn is to check that the kernel of Q is isomorphic to bigger 1. And that's very easy. I don't want to go very technical. The proofs are already written down. It's accessible, it's published in open. So I will tell you the important facts here. P and Q are very symmetric. Both their composition is commutative and produce another projection whose range is one-dimensional. This fact and the fact that bigger 1 is primary let us prove that the range of Q contains a complemented copy of bigger 1. And applying the composition of Pelczynski, you prove that finally, eventually, the range of Q is isomorphic to bigger 1. And in this case, the proof is already over. And let's go for the funny general case. Consider an infinite dimensional reflexive subspace X of L1. Here, omega sigma. Okay. In this case, omega is already the unit interval. Okay. Sigma is the Boelian sets and such. So, I'm going to give the idea of the proof. Oh, sorry. From our result by Aldous, it is known that the subspace X contains a normalized basic sequence equivalent to the unit vector basis for some reflexive little LP. That means P greater than 1. So, it is also very well known that bigger 1 contains a sequence of p-stable independent random variables. P-stables is saying that the distribution function is exponential of minus t raised to the power of p, etc. Okay. The important fact is that the sequence is p-stable, then the subspace span, actually the sequence Rm is isometrically equivalent to the unit vector basis of little LP. So, if we map each function Fm to the corresponding function Rm, this mapping is an isomorphism, a bijective isomorphism. Of course, the span of Fn and the span of Rn embeds isometrically in bigger 1. So, if we could extend that isomorphism T to an automorphism from bigger 1 to bigger 1, the problem would be over because the sequence Rn, as proved in the previous case, has a good splitting in bigger 1. So this good splitting induces a good splitting via the automorphism G for the sequence Fn. That's the idea. So the problem is that this is not very easy. It's not very easy to get that automorphism G, but if we produce a change of density on the measure mu, we can get an isometrical embedding of certain functions Rm isometrically equivalent to the unit vector basis of little LP. And since G is an automorphism, the same argument that I just told works to here. The good splitting of Rn in bigger one, in this bigger one, has a good splitting. That's why I needed in the previous case that generalization to a probability measure different from the Lebesgue measure. So this good splitting here of the sequence Rn is transmitted by the automorphism G to bigger one, so we have a good splitting for this sequence Fn in bigger one, and that ends the proof. So all business about is how to get this automorphism G. For this, let me recap. Take again the subspace X, which is reflexive. Take the sequence equivalent to the unit vector basis of little p, a normalized sequence in X. And then, from an argument that I'll tell you later, there exists a magic density. A density is a function, a positive function whose interval is just 1. Here, for simplicity, I will assume that that density is not null at any point omega. After this assumption, I mean, it's not without loss of generality. You know this. I mean, if the function p is null in some places, then you have to work with more perturbation stuff and such. But for the essence of the proof, let us assume phi is not null at any point. So, in this case, we can calculate the weak limit of the sequence exponential ITFN. The limit is this function, which depends, is a function x depending on the parameters t and omega. This function is called the limit conditional characteristic function of the sequence Fn. So, we proceed with the automorphism G. To get G, what this automorphism G, sorry, again. Oh, okay. This function G maps every function f to the quotient f over phi. That's why I need phi to be not null at any point. Okay, then the change of density here, this is the measure p by the Lebesgue measure mu. So this mapping is a bijective isometry. No problem. Then, if we take, for some subsequence of Fn, we take its image by the automorphism G, and this sequence has weak limit, the function ht omega, it is here, which does not depend on omega. That's, exactly, on omega, which is an important fact. This function here is the characteristic function of a p-stable random variable. So, following an argument by Berkes and Rosenthal, it can be proved that there exists a sequence of p-stable independent functions Gn in bigger one after change of density, for which some subsequence fkn over phi minus Gn, well, the corresponding series that you have here is convergent for almost every omega. And from here, and taking in account that X is reflexive, so its wall is equinterable, we can pass to another subsequence of Fn. I used exactly the same notation, so that the series of this norm after change of density is convergent. That's an important point, because refining the subsequence, you can get that the value of this series is as small as you want. So the best case is when n is just 0. This is a very favorable case. So since this is a sketch of the proof, let us assume we are in this favorable case. Assume m is just 0. Well, in this case, we take the proof of the case T21 for independent random variables with 0 mean. So L1 after change of density has a good splitting for the sequence Gn. So since G is an automorphism, an isomorphism, a bijective isomorphism from L1 to L1 after change of density, this isomorphism induces a good splitting for the sequence Fkm. And the proof is over. That's the end. So in case m is not null, then we have to work with more perturbation arguments, and it introduces some obscurity on the proof. So I prefer to explain only this case. So now is the time to explain where does phi come from, the change of density. So if you take the ultra power, any ultra power of big L1, it can be proved that it consists of a diaxom of big L1 with the ultra power of the measure of mu. I don't need to explain which is that measure. The only thing we need to know is that this measure is a probability measure without atoms, plus another L1, which we don't care much about it right now. L1 is canonically contained in the first summand of this diaxom, so it's also canonically contained in the ultra power of L1. Ultra power of L1 is actually a quotient on the space of bounded sequences of L1. And so consider the subspace E, which is the span of those functions Fn which were equivalent to the unit vector basis of LP. So from a result by Cania and Krivine, we can find an ultrafilter U on the positive integers and a density function phi, that is a positive function with integral 1, an element V in the first component of this ultra power. So this element V has a representative in the ultra power, because I told you this is a quotient of the space of bounded functions of L1. So we take a representative, an equiintegrable representative of V. So this function V is P stable with respect to the measure ultra power of mu. So taking the product V by phi, where phi is here the canonical immersion of phi into the ultra power of L1, this product belongs to the power of the subspace E. That's important, since E is reflexive. This ultra power is contained and entirely contained in the first component. So Cania and Krivine also proved that the sigma field generated by this variable V and the Borelian sets canonically embedded in this ultra power are independent. So, making some computations, it can be proved that the conditional expectation of this exponential with respect to the Borelian sets is this function. It's exactly the limit conditional that appeared in the slide before. The next step is very easy. It's almost trivial. You translate the from the language of probability to the ultra power setting, and you get that this sequence is weak convergent following the ultrafilter U to the functions ht omega, that the function that appeared in the slide before. So at this moment, we can claim yet that this function is the limit conditional characteristic function of this sequence phi by Vg, because for that, we would need that this convergence, this weak convergence, would be a convergence in the normal sense of the sequences. But what we have here is a convergence following an ultrafilter. But from here, we can prove that there exists a subsequence of the functions Vj, which indeed converge weakly in the sense of the sequences to the functions ht omega. This step actually is highly non-trivial, in my opinion. Why is non-trivial? Well, first, it's very tempting to apply that if it's the case that U, the ultrafilter U, da Cunha, be a selective ultrafilter. A selective ultrafilter is an ultrafilter with very wonderful properties for convergence of subsequences. But we can't do that. First of all, the existence of selective ultrafilters depends on adopting the continuum hypothesis of Martin axiom, which I know you like very much here. But even accepting Martin axiom, the problem is that the ultrafilter provided by da Cunha-Castell is a product of ultrafilters. And in that case, you can't be at all a selective ultrafilter. So you have to work, to do a hard handwork in order to get finally this convergence, this weak convergence in the normal sense of the sequences. And from there, taking the representative Cj, you prove that this sequence converges weakly to the functions ht omega, which is what we have induced in the previous slide. So the proof is already completed. And well, that's the end. And since the result is already published, so if you want to know about a few misprints, more than in the abstract, you have here a short list of them. And thank you very much for your kind attention.
I'm extremely happy to introduce to you William Corrêa, that will talk about the interpolation of Orlik spaces and the extension property of operators into spaces of continuous functions. William, up to you.
Thank you very much. Thank you for organizing. I would like to thank Alberto, but he's not here anymore. I want to start my talk by remembering the definition of a quintessence. We have already seen it here, but I want to remember it. So given two Banach spaces, Y and Z, twisted Banach space, twisted sum of them is a Banach space X, which appears in the middle of a short exact sequence like that. So it basically says that Y is isomorphic to a subspace of X, and the respective quotient is isomorphic to Z. In the particular case where the Y and Z are L2, and the middle space is not L2, we'll say that X is a twisted Hilbert space. Well, a separable one, but today, like Antonio, I believe we will forget about anything that is not separable. So of course, once you have a definition like that, you must ask, is there something that satisfies that? And the first example of a twisted Hilbert space was given by Ansel, Lindenstrauss, and Pizier in 1975. And their construction was local in nature. Their space is of the following form. It's an L2 sum of finite dimensional spaces. When these finite dimensional spaces are a thick step farther from being Hilbertian. But today, we will be more interested in the example of Calton and Peck, which was a global construction. They considered for a given vector of finite support the following method, which is the Calton-Peck method. Kp of x, so this x is a sequence xn, will be the sum of xn log of modulus of xn over the 2 norm of x times n. So we see here an entropy function placed on rho, and they define for a pair of vectors of finite support the following quasi-norm. The quasi-norm of a point yx at the Calton-Peck space will be the 2 norm of this difference plus the 2 norm of the second vector. And like I said, this is a quasi-norm, so we don't have here a triangle inequality, we have a multiple of it. Have norm of 1 plus 2 is smaller or equal to a constant times the norm of the1 plus the norm of the 2. But at the end of the day, this is not some problem because this quasi-norm is equivalent to a norm. So we take the completion of it, and if we take the second coordinate to be 0, this part here disappears. So we are only with y, the norm 2 of y. So this subspace of the first coordinate, the second coordinate 0, is isometric to L2. And if we fix x and take and change y, we could take y to be Kp of x. Then the infimum will be the L2 norm of x. So the quotient is L2. And this is not isomorphic to a Hilbert space because the way this map is built, we can, for example, ensure that the type of this space is not 2. Okay, so now we have at least 2 examples of twisted Hilbert spaces. And actually one can build many more. So the next step is trying to classify them. We can start to ask what kind of properties they must have, which they must not have, and which they might have. So for example, properties that they must have. They must be reflexive, since being reflexive is a free-space property. Being L2 saturated is also a free-space property. So every infinite dimensional subspace has a further subspace isomorphic to L2. They must have type P for every P between 1 and 2, 2 not included, and cotype Q for every Q strictly bigger than 2. These are properties that those spaces must have. Some that they must not have. Calton showed that they must not have an unconditional basis. If it had an unconditional basis, it would be the Hilbert space. They must not have type 2, and that is a consequence of Morey's extension theory. So it had here L2, X, L2, and take the identity here on L2. So this is a cotype 2 space. If X had type 2, then we would be able to extend the identity. So this would be a projection on L2. So X would be the direct sum of L2 and L2. It would be Hilbertian. For the same reason, it cannot have type 2. You dualize the sequence and apply the same argument. Okay, so these are properties that they must have, properties that they must not have, and there are properties that they might have. For example, they might be or not weak Hilbert. So I will not give the exact definition of weak Hilbert, but you might think of it as the following. Finite dimensional subspaces have big subspaces that look like L2. So Jesus Suarez showed an example of a weak Hilbert, twisted Hilbert space using the two-convexification of zero-sum space. And for example, the Calton-Peck space is not a weak Hilbert space. Asymptotic Hilbert. So The definition looks a bit like with Hilbert, but instead of looking at finite dimensional subspace, you look at finite codimensional subspaces. So Jesus Suarez and Daniel Morales also showed examples where this happens and where this doesn't happen. And the property that we are interested in today is the C of 01 extension property. So the C of 01 extension property is a property of pairs of spaces. So you have a pair Yx, where Y is a subspace of X. And it basically says that every operator from Y into C of 01 can be extended. So you have here an operator T, and you cannot extend it. And in the particular case where we are looking at a twisted Hilbert space, we are looking at a particular copy of L2 inside of it. So we say that the twisted Hilbert space has the C of 01 extension property if the pair L2X. So examples. Carlton shows that there is a twisted Hilbert space without that property. And it's a beautiful result that uses many things from complex interpolation from the theory of UMD spaces. And at the end of the day, I think one of the most beautiful parts of it is that it doesn't give you the example interface. It says, here are two examples of twisted Hilbert spaces. One of them must not have the C of 01 extension property. You don't know which, but one of them must not have it. And quite surprisingly, the Cal-compact space has it. And one of the reasons that it has it is that it is a Penchel Orlick space. And that's the reason I want to explore a bit today. So that we all are in the same page, I will remember the definition of an Orlick space. So we take a real function of the positive real numbers, which is convex, non-decreasing, at 0 it's 0, and at infinity it goes to infinity. So for example, something like this. Once you have it, you can build a sequence space, the associated Orlick sequence space. So it's the space of all sequences of real numbers for which there is some positive row satisfying this. You take big row, for example, and you diminish your sequence modulus, and you sum. This series must be bounded by 1. And your norm is the increment of those rows. And the classical example is taking your Orlick function to be T to power P, and the corresponding Orlick sequence space is LP. Okay. Another example that I find interesting is if you take phi of T to be T3 squared log of T3 squared. At least on a neighborhood of 0, because it appears as a subspace of the Cal-compact space. And it's a very important subspace of it. Penchel-Orlick spaces are generalizations, is a generalization of this concept to higher dimensions. So instead of taking a function of the positive real numbers, you take here a function on Rk for some real space. And then your function will be called a Young function if it is even, convex, phi of 0 is 0, and it goes to infinity at lines. Okay. And then you define an associated Penchel-Orlick space in exactly the same manner as you did for the Orlick space. And here are the examples, sort of. I will explain why they are sort of examples, which is the following. If you take this function, psi p of yx, to be modulus of y minus x log of x to p plus modulus of x to p, the associated Penchel-Orlick space will be this Cal-compact space. So I only did the Cal-compact space, which is a twisted Hilbert space, but you can modify it by putting here the p norm, and you get a twisted grouping of LP, which is non-trivial. So this space is not isomorphic to LP. And this is a sort of example because this function is not really a Young function. This function fails to be convex, but it has a close enough property. It is quasi-convex. So the following. So instead of having convexity, we have here a multiplicative constant. If you have a function like that and do the construction of the Fench-Orlick space, you get a quasi-norm. But at the end of the day, it will be equivalent to a norm. Okay? So an important thing that we see here, this x minus log of x corresponds to the Carlton-Peck model, where we have this x log of x divided by the 2 norm. So we just deleted the 2 norm here to get this function. So it appears very naturally in the construction. Okay. And the fact is that if you have a Fench-Orlick space, you automatically get the C of 01 extension property. So if you have a Fench-Orlick space defined by a non-degenerate function, and non-degenerate here means that it's 0 only at 0. Then if you take any subspace of it, the pair of this subspace with the Fench-Orlick space has the C of 01 extension property. So we have plenty of this property here appearing. And what was my goal here? My goal was to extend this result to further twistings of my twisted Hilbert spaces. So one can go one step further and twist the twisted sums. Okay. So it's a result by Cabello Sanchez, Castillo, and Carlton that there is, So here I changed a little notation. Instead of noting the Carlton-Peck space by V2, we'll denote it by R2 so that we don't confound it with Z4, which was the twisted version of L4. Okay. So there is a space R4, which is a twisted sum of the Carlton-Peck space with itself, but is not a twisted Hilbert space. So being a twisted Hilbert space is not a free-space property. And more generally, we actually get a family of spaces that connect as twisted sums here. So for example, you get a twisting of this R4 with itself, or of this R4 with R2, or R4 with L2, and so forth. And my questions were, this subspace here with this superspace, does it have this C of 01 extension property? And more specifically, is this space a Fench-Orlick space for each n? Because if it was, I would get automatically the C of 01 extension property. Okay. So I just repeated here the questions and the possible strategy. So I didn't tell you because I forgot, but the ones who proved that the Carlton-Peck space is a Fench-Orlick space were Androlax, Kazaku, and Carlton. Okay. So the first strategy would be to reproduce their proof of this result. But we face here a number of problems. The first one is that the proof is rather technical. Okay. And it depends a lot on the particular formula of quasi-norm on R2, on the Carlton-Peck space. So like I said, the Young function that they use is the following. Psi p of yx is modulus of y minus x log of x squared plus modulus of x3 squared. And we see that it came directly from the definition of the Carlton-Peck space. It came from this map. We just deleted the 2 norm here. So it depended a lot on you being able to see, to stare the face, which was the quasi-norm. Okay. And what they do is, once they see naturally what should be the Young function, they do a bunch of calculations and show that this Young function gives you the Carlton-Peck space. So the first thing is that if we would like to reproduce the proof, we would have to stare the face of the quasi-norms. And of course, we have infinite spaces. We cannot do that. And even if we could, if I gave you the quasi-norm for one of those spaces, then you would have a hard time proving directly that it gives you a quasi-Young function. So we'll give you the quasi-norm on the twisted sum of the Cal-compact space, so you see what I mean. So this is the Cal-compact map, except there is a 2 there appearing. This is this map with a 2 for technical reasons. And given a pair of sequences which are finitely supported, you define this map. So here we see that there is a Cal-compact map appearing. There is a log2 square of the Cal-compact map. So there is a log2 square of the log. Here there is a log2 cube to the power 3 and so forth. And that's not enough. We still have to put that inside the norm of the Cal-compact space. So if I tell you, see, this will give you naturally a pentaorthogonal space. Now prove it. You would have a hard time doing that. And if you grow here the number, I suspect that the time it would take to prove that it is a pentaorthogonal space would grow exponentially in time. In N. Okay. So we did a new strategy. And the new strategy is to see where those spaces come from. And they come from complex interpolation. There is a beautiful theorem from Rees and Thorin that says that if you have an operator from LP0 to LQ0 and from LP1 to LQ1, a bounded operator on both those cases, you can interpolate them. You get that T is bounded from LP theta to LQ theta, therefore theta between 0 and 1, and where those P theta and Q theta appear as combinations of those numbers. Okay, so it's an interpolation theory. You don't need to look directly at those spaces to get boundedness. You look at those extremes, and many times it's easier to look here than looking here. For example, if this was L1, this was L2, it's easier to get access to the norm. And interpolation tries to reproduce this behavior. So we have a pair of spaces x0 and x1. We also have another pair, and we want to find interpolation spaces. We want to find spaces that reproduce this behavior. There are many methods to do that, and the proof of the restoring theorem motivates one of those methods, which is the complex interpolation method, which for each theta between 0 and 1 gives you an interpolation space. And the basic idea is that you take the strip in the complex plane of complex numbers with real part between 0 and 1, and you make an analytic function on this Banach space with imaging this Banach space, which we will not care about now, which one is. But the thing that at the left, x0 will appear, at the right, x1 will appear, and your interpolation space will be what appears here at theta. So at theta is the image of those functions at theta, and the norm is a quotient norm. It's the infimum of the norm of the functions that realize that point. And for example, if you take LP spaces and do complex interpolation, you get LP back. So you get the restoring theorem back. And more generally, if you get a pair of cut function spaces, which are a particular class of Banach lattices, then complex interpolation gives you a geometric mean of those spaces. Okay. Now, how does this where does the Cal-compact space appear here? So we use here the image of those functions, but those functions are analytic. What can we do if we take advantage of that? What if we use the derivatives? So instead of looking only at the images, I will look also at the derivatives and take also a quotient norm. Okay. And what happens is that looking at this space where I take the image and the derivative, this space is a twisted sum of my interpolation space. And for example, if I take the pair L infinite L1, interpolate at 1/2, I get L2. And the corresponding derived space is the Cal-compact space. Okay? So we see here that the Cal-compact space has this deep connection with interpolation theory. Well, but again, those functions are analytic. why should I stop with just one derivative? I could look at Taylor sequences here. I could put more derivatives and put the quotient norm as well. And what happens is that I get a family of twisted sums. Okay, so I get this space dn of x theta where I go until the nth derivative, and all those spaces are connected through twisted sums. And for example, if I take the pair L infinity L1 at 1/2, I get L2. The derived space is the compact space, and that space R4 that I mentioned before, which is a twisted sum of the compact space with itself. For what? Here. No, no, it must be the third, because you must have 4 points, right? Okay. Okay, so using this now, I can get a generalization of the result about C of 01 extension. So for each n bigger or equal to 1, those generalized compact spaces are tensor-ordered spaces. And more generally, if I start with a pair of ordered functions satisfying some properties, the interpolation space is again an ordered function, and the derived spaces of all orders are tensor-ordered spaces. So I get automatically the C of 01 extension property. Okay. And the idea of the proof is, okay, my spaces were defined through a quotient norm. So I got here something like that. Norm of x was the infimum, a norm of f, such that f of theta was something, f prime of theta was another thing, and so forth. Okay. Now, in this particular case of ordered sequence spaces, I can give you explicitly what should my function be. What should be a function which almost realizes this norm. And for the next levels, I can use those functions of the first level to build the next ones from the next levels. Okay. And doing that, I have an idea of what should be my Young function. And now there is no escaping. I still must use technical things. I still must do a bunch of calculations, but I have another advantage now, which is analytic function. It's theory. I can use the whole theory of analytic functions to help me to prove that those give you Young functions. So the main ingredient that I use is the following. We have here an analytic function on the street to the complex numbers, and Hadamar's 3-line theory gives you the following: that the modulus of theta is smaller or equal to the sup at t by f of yt. So the sup at the left, 1 minus theta, times the sup on the right, to theta. So the values here are dominated by a geometric mean of the extremes. Okay, this is the main tool that I use to show that those functions are indeed Young functions. Okay. And to finish, I would like to share with you some open problems. So the first one is, under what conditions on my spaces at the end of the scale, so I will interpolate them, x0, x1 at theta will give me at theta, and I have the derived space. So I put here that the derived space has the property, but should be the pair. Okay, the pair x theta, dx theta. Because I have here my twisted sum. So under what conditions does this pair have the C of 01 extension property? And once I know that the first one has the C of 01 extension property, can I get that the next ones will have it? So for example, this question is motivated by the following. If this space is not complemented here, then the next ones cannot be complemented. So from the first twisted sum, you get information about the higher ones. And to finish, if I start with facial order these spaces here and interpolate, what do I get? And this question is motivated by the following. Together with Jesus Castillo and Felix Cabello, we showed that if you take the complex spaces, you take a ZP0 and ZP1 and interpolate them through complex interpolation, we will get a complex space back. Okay. So since those spaces are facial order space, you get an interpolation scale of facial order spaces. And this is somewhat surprising because we basically only know how to do complex interpolation of Banach lattices and a particular kind of cut function spaces. So we have here new examples of interpolation scales which are not of Banach lattices. So can we generalize that? Can we use facial order spaces, interpolate them, and get facial order spaces back? Thank you.
Okay, thank you for a nice talk. This is about your notation and it's probably very trivial for the experts, but you have two indices like M and N, right? And I can see when you defined R4, that was a twisted sum of R2 with R2.
Yeah.
And 2 plus 2 is 4, and it doesn't matter which one is the left and which is the right.
Yes.
Now 1 plus 3 is also 4, or 3 plus 1, and it matters which one is first and last, right? But is this consistent? In other words, if you take the twisted sum, say by what you call R1 as the subspace and R2 as the quotient, or the other way around, you get the same space?
Yes, you get the same space.
Right. Is that clear?
It depends on what you call clear. Okay. So if you see the proof, it's pretty clear. I don't think there is many magical things happening there. But
Sure.
Yeah, there is some work to be done.
Sure. And the same applies for your derivatives, presumably, right?
Yeah.
Yeah. Okay, thank you.
More questions? More remarks?
So from the Carlton result, that one of those spaces had to fail this C1 extension property, and your result that says that, if I understand correctly, every decent interpolated space between L2 and between L1, or every twisted sum of reduced sum of L2s which appear as an interpolation scheme in some decent conditions have the C01 extension property. So at the moment, we still do not know any complete example of a twisted sum of L2 with L2 which fails this C01 extension property. Is it correct, or?
We know about Carlton, like I said, Carlton gave an example, but it's an indirect example.
So we don't know which one.
We don't know which one of them is.
So this is still, I mean, this hasn't been improved until now.
That I know now. You know, and it's concrete example, like you know. So what he does is basically the following. He gives you to start twisted sum of L2, where here X is not a UMD space.
A what, sorry?
A UMD space, uniform martingale difference. And this is not your example yet. So you take the dual. This is not your example yet. You take now an L2 of them. So now through Carlton's magic, he says one of those must fail the C01 extension property. Okay.
Thank you.
Any other questions? Okay, then let's.
But this Carlton example, I mean, so does it have, it does not come from interpolation, this year?
The first one that I said that the middle one is not even space, I think comes from interpolation. Yes, almost certain.
Are we ready?
I'm ready.
Then, like you, the best is yet to come. So, our last speaker is Ms. Laustsen. I'm fascinated with this title, Split Teams. Because if you say splitting of extensions, there are several splittings, different. I'm fascinated with that. Okay, he will talk about the splittings of extensions of the algebra of bounded operators on a Banach space. Okay.
Okay, thank you very much, Jesus, and thank you very much to all the organizers for the opportunity to speak here. So what I'm going to talk about is joint work with my former student, Richard Skillicorn, and also some of it a student from former back that we, of course, all heard this morning, Tomasz Kania joined us as well to solve the last outstanding problem that we had. So I would like to dedicate this talk to the memory of two very important mathematicians that influenced this work. So the first is Charles Reid. Basically, everything we do built on a very clever Banach space as he constructed. And even if you don't care about the splittings of extensions of algebras bounded operators, then I hope that Banach space, I don't think it's received as much attention from the Banach space community as it might deserve. So I hope that might be of interest to some people. And the other one is Garth Dales, who sadly passed away in October. And he's the one who basically asked us the fundamental question that we based this research on and that we were pleased to say we answered fully. So I'd like to, as I say, dedicate this talk to their memory. Anyway, so I'm very naive on these math-out diagrams. I'm definitely not a fully signed up member of the club yet. But so for me today, an extension will simply be a short exact sequence of that form there. And the object I'm interested in is basically, I mean, when I say an extension of a Banach algebra B, that would be the quotient in my short exact sequence. And to simplify, so of course now I don't talk about a subspace here, I talk about an ideal, and I simply think that that is the, I mean, this map here is actually the embedding. So as I say, to get my extensions, I'm really looking at continuous surjective algebra homomorphisms onto my Banach algebra B. And so now I've changed the category slightly, right? I'm working in the category not of Banach spaces, but of Banach algebras. Okay? And always when I say homomorphism, I mean an algebra homomorphism. All right? So the key terminology that I'm going to use, well, the first bit is that you call the extension singular if the ideal here has the trivial product. So any two elements just multiplied to 0. If you wonder why am I interested in that, the honest answer is I'm not entirely sure, but people who do homology of Banach algebras or indeed general algebras, I mean genuine algebraists doing homological algebra, they like that condition because it helps with some higher homology constructions, I believe. So that's apparently a good thing, not a bad thing. You might think having the trivial product should be a bad thing and we should avoid that, but actually it drops out from our construction, so we might as well flag it up, right? Okay, so the second point is that I'll say my extension splits algebraically if it splits in the category of algebras. So in other words, my quotient homomorphism, if you like, phi here has a right inverse. I can go back from B up to A, or in other words, you have a left inverse of the this one here, but I don't assume that homomorphism is continuous, all right? And then you have the strong splitting if your right inverse is not just an algebra homomorphism, but it's a continuous algebra homomorphism, or in other words, if your short exact sequence splits in the category of Banach algebras. So that's sort of the proper categorical notion of splitting in this context. And this is why splitting was in plural to start with, because I'll have certain kinds of splittings, but not other kinds. That would be the name of the game here. All right. So, and the final one is the one you're familiar with, namely, we say that the short exact sequence is admissible if phi over here has a right inverse that is bounded and linear, or in other words, if the kernel of phi is complemented as a Banach space inside A, or, I mean, in other words, my short exact sequence splits in the category of Banach spaces. And as I said, the reason I'm using this terminology, well, this is what people usually use in Banach algebra theory. So for you, admissible is a natural notion of triviality or split or whatever you want to call it, right? And of course, this is the fine form, right? If you split strongly, then you both split algebraically and you are admissible, but not necessarily the converse. And this is essentially the topic of the talk. All right. Any questions about that? Good. Okay. So the sort of starting point of this, a systematic study of extensions of Banach algebras from this point of view, was done by Bill Bardet, Garth Dales, and Zina Likova in a memoir of the AMS that eventually appeared in 1999. And they studied essentially two questions for various classes of Banach algebras. So the first is whether if you have an extension which splits algebraically, does it also split strongly? You know, that's a kind of automatic continuity question, right? Because you assume you have an algebra homomorphism from the quotient back into the algebra in the middle, and you then ask, can you also always find a continuous one? And the finer version of that is that you add the word admissible. So in other words, you assume that the splitting somehow in the middle happens also in the category of Banach spaces, and then you ask the same question, all right? And as I say, I mean, well, Bill Bardet is sort of one of the grand old men of automatic continuity theory in Banach algebras, so it was very natural for this set of authors to consider these kind of automatic continuity type questions. Okay. So let me just remark that if you know that all homomorphisms from B into a Banach algebra are continuous, well, then of course there's no problem here, right? Because then as soon as you assume you have an algebraic splitting, then the homomorphism that splits is automatically continuous, so you have a strong splitting and you're done. So in other words, we are immediately forced to consider Banach algebras that admit discontinuous homomorphisms. All right? And well, this is a conference for people interested mostly in Banach spaces. So my focus here will be on what I call B of E, so the bounded operators acting on a Banach space E. All right. And that's why I've called, incidentally, my, I mean, the sort of the algebra I'm looking at extensions of B, because that will always be B of E here. All right. So basically, so because we need to look at discontinuous homomorphisms necessarily in order to address this problem, well, let's just review the history of continuous automatic continuity of homomorphisms from B of E. And the classical result is due to Barry Johnson, not Bill Johnson, of 1967. Barry Johnson showed that if you have a Banach space which is isomorphic to its square, or slightly more generally has a so-called continued bisection that enlarges the class slightly, but don't worry about the technicalities, well then every homomorphism from B of E into a Banach algebra is automatically continuous. So in other words, to get on with our question, we are forced to consider Banach spaces that are exotic in the sense that they don't satisfy that condition. All right? And well, of course, most classical Banach spaces do satisfy that condition. The standard exceptions that were already known at the time when Johnson proved the result are the quasi-reflexive James spaces and the continuous functions on the ordinal interval up to omega 1. So that's my C of K space for you. I will not be a lot of C of K spaces, but there will be a few diagrams here at least. All right. And well, unfortunately, those sort of semi-classical Banach spaces, they are not good enough to help us either, because it's known that homomorphisms from B of E into a Banach algebra are also automatically continuous in those cases. So this is sort of comes out of the work of Loy and Willis. And then Willis on his own, and then also Katie Ogden, a student of Garth, did the final bit there. Okay, so we need to look elsewhere, and this is where Charles Reid comes onto the pitch. So around the same time as Loy and Willis did their work, Charles Reid constructed an example of a Banach space that I will call E subscript R in honor of Reid, that has a property that B of ER admits a discontinuous homomorphism into a Banach algebra. In fact, what Reid constructed was far stronger than that. It has a so-called discontinuous point derivation, but I don't want to go into that. So let me just tell you what the key technical aspects of Reid's construction were, out of which the existence of the discontinuous homomorphism falls very easily if you know how to do these kind of things. But the point is that it's the key technical aspects that we are going to focus on here. All right. So the idea is that B of ER contains a closed ideal of codimension 1. That ideal contains the ideal of weakly compact operators, which has infinite codimension. And now the magic happens that whenever you take two operators in this co-dimension 1 ideal, so the big ideal, you multiply them together, or in other words, compose them, and then you end up in this ideal of weakly compact operators that has infinite codimension. Okay? So in other words, the product on I is very degenerate, right? Things collapse a lot. This is sort of this is the headline here. It doesn't matter, by the way, that it's the ideal of weakly compact operators, but since it is, I thought I might as well use its proper name here. Okay? So, if you thought that was a bit confusing, let me now show what the starting point of what Richard Skillicorn and I did, which was to sort of strengthen it, and this will be in a way that I think will be much more attractive in the eyes of this audience here. So let me write L2 tilde for the unitization of the Hilbert space little l2 endowed with a trivial product. Okay, so that just means that I add one extra dimension, which I call k times 1. So k is my scalar field. Could be either real or complex scalars as you wish. Okay, I put the one norm on here. So I just take the L2 norm of the L2 part and then the modulus of the scalar. And my product here is that the sort of the Hilbert space parts multiply to 0. And then I treat this 1 here as a formal identity. And then I multiply out the brackets the way they should, okay? So that's a unitization, a special case of how you unitize a Banach algebra, of course, okay? But that's what I mean with the 0 product here. And once I've done that, now I can explain to you a sort of strengthening of what really, if you sit and study the details of what Reed's construction did, then you will get a very nice split exact sequence here. So basically what Richard and I worked out was that you can find a continuous surjective homomorphism beta from all the operators on ER onto L2 tilde, this unitization of the Hilbert space with trivial product, with the property that its kernel is the ideal weakly compact operators, and then when you then write down the corresponding extension, it splits strongly. All right. So what that says, in other words, is that B of ER is what's sometimes called the semi-direct product of L2 tilde and W of ER, meaning that WER here is complemented as a Banach space here, and actually the complement, which is L2 tilde, is not just a subspace, it's actually a subalgebra. Okay, and the reason we get the trivial product of L2 here, right, that was this fact on the previous slide, that every product of pairs of elements from I, they went into the weakly compact operators. So that's somehow what captures this. And obviously I have to add an identity here because if I have a surjection from a unital algebra onto anything, it must map the identity to an identity. So that's why I must map the, join this identity to little l2. But really, little l2 is somehow the image of this cofinite ideal I had on the previous slide. Okay, so this is effectively what Reed's, the summary of what Reed did, and you have to do some extra work in order to understand that, and then you can get this result out of it. Okay, so, well, now we want to stare at some diagrams, but if you haven't fully paid up your subscription yet to that club, let me just remind you of the pullback construction. So you have three Banach algebras, A, B, and C. You have homomorphisms, alpha from A to C, beta from B to C, and then a pullback is a triple consisting of a Banach algebra D, a homomorphism gamma from D to A, and a homomorphism delta from D to B, which satisfy that they make the diagram in here commutative, right? So the pullback sits up here. This is sort of the bit you're given. So from A into C and B into C, then you get the pullback sits up here with these homomorphisms there. And the universal property says that whenever you have another Banach algebra E and homomorphisms eta and psi that make this bit here commutative, then you have a unique homomorphism from E to D here that makes everything commutative. All right. But I expect by now that everyone will have seen this so many times that this is fine. However, it seems to be surprisingly underused in the context of Banach algebras. I hadn't really seen anyone making serious use of it before we used it. So we just checked everything worked by hand, and it does. All right. So now let me try here to see. So this is the staring at diagram part. Okay, so suppose we have three Banach algebras, A, B, and C, and we have extensions. So basically in the first one, A is in the middle, C is the quotient, and alpha is my homomorphism. In the second, B is in the middle, and C is the quotient again. Okay, and then I can do, so now I can do my pullback construction, right? So I have my short exact sequence. Let me just try and write it. So that's beta. Okay, and then I say, well, I have now a short exact sequence here with alpha coming on to C and some Banach algebra A there, and its kernel up here. And if you haven't been completely asleep at this conference, then you will know that the thing you want to do here, right, is you will want to do the pullback there. Okay, so you get the pullback and then you complete the diagram. And so this map here, that will also be a surjection. So you get a short exact sequence over here. All right, and now, so that's basically what comes next, right? So I take this, the pullback, I get my short exact sequence, and well, then you check that how things work out. So basically, if my sequence up here, so this guy here is singular, then this is singular. Remember, this just means that if you have zero product here, you must have it there as well. That's because the two are isomorphic, so that's very easy. Then, on the other hand, if you know that okay, so now we assume that this sequence here splits strongly, okay? And this is because, so in my application of this result, this one here will always be played by my the one I started with, the one we had on the previous slide. So this will be B of ER, the bounded operators on read space. This will be L2 tilde that we quotient out, okay? And then, so this is where we're starting from, all right? And then let's see. Now the idea is that so we know this guy splits strongly, and then basically the idea is that if this one splits strongly, then so does this one, and vice versa. All right. And also you can say the same if this one splits algebraically, if and only if this one splits algebraically. And also this one is admissible, or in other words, splits as in the category of Banach spaces if and only if this one does. Okay, so basically the idea now is I want to try and see that I have an extension with B here, B of ER being the quotient algebra. Okay, and I want to find one that does not split strongly, but splits algebraically and possibly is admissible as well. And the idea is I want to do that by constructing such a sequence over here instead. That's somehow the principle of this talk. Okay. So, okay, so this is, as I say, this is this sequence here. That's the one that sits here at the bottom. All right. And so the idea is that if B of ER, B, which is this guy, right, has a singular extension which splits algebraically, but not strongly, if and only if my quotient, which is L2 tilde, has a singular extension which splits algebraically, but not strongly. And similarly, if I throw in the word admissible, the same happens. And as I say, this is simply by transferring between these two sequences, right? So this one has whatever property if and only if this one does. Okay, and the motto here, the idea is that it's far easier to construct extensions of L2 tilde. This is a very simple Banach algebra than it is B of ER, which is a very complicated beast. Okay, so that's somehow what we're trying to do. Okay, and as I say, the aim is to show that both of the above statements are true. Now, the statements are to some extent formulated in the negative, right? They're counterexamples to the general question by Baudet, Dales, and Likova. We're showing that in the category of, or in the collection, in the class of Banach algebras of the form B of E, we do have extensions which split algebraically but not strongly, and even admissible extensions which split algebraically but not strongly. All right. So, as I say, that will answer those questions in the negative. All right. Any questions so far? Good. So, okay, the first question, so this is this one, the first bullet point there and the consequences is relatively easy to do now, because I just take a bounded linear surjection from little l1 onto little l2. Okay, I put the trivial product on little l1. Well, then Q is obviously a multiplicative map, because both sides have the trivial product, and then I have a singular extension there. All right, singular, remember, just means that if I have the trivial product here, I also must have the trivial product there. So that's totally obvious. Of course, it cannot split in the category of Banach spaces for all sorts of reasons. So that's fine. All right. But therefore, if it doesn't, if it's not admissible, then of course it can't split strongly either, right? Because if you split strongly, then you're certainly admissible. Then I mean, then L1 would split as a direct sum of Banach spaces, the sum of two. Okay. On the other hand, it splits in the category of vector spaces, because everything does, right? We're now just saying that if you have a linear map between two vector spaces, you can always find, as a surjection, you can always find a right inverse, okay? So we have a linear right inverse, say, call it rho, and rho, of course, is trivially multiplicative, because again, it maps between two vector spaces with trivial multiplication. So I have an algebraic splitting. Okay, and now, well, this wasn't quite what I needed. Now I just adjoin identities here, which just means I adjoin a formal identity to L1 here, I adjoin a formal identity to L2 here, and then I let Q be unital. So I take the identity here to the identity here, and then, of course, that doesn't change what the kernel will be. All right, and then I have solved my problem. So that was pretty easy. Once you had the machinery and once you had this very clever Banach space of Charles Reid. All right. Now we come to the second question. That requires a bit more work. Let's see how we're doing for time. All right. Okay, good. So the second question. So now I mean, remember in this construction here, the key point was that this extension here couldn't be admissible. I mean, in other words, L2 is not complemented as a Banach space in little L1. Okay, that was a key observation, essentially. So now, of course, I can't use that anymore. So I have to work quite a bit harder to do that. And this is where Tomasz joined us, by the way. So the previous part, so that was what where Richard and I did for the first round. And then the second round here is where Tomasz also came along. So let's see. So let's just start with a Banach algebra and a Banach A bimodule X. Okay, so this is like a general construction I want to show you, and eventually I will get to the point where I can construct my suitable short attack sequences. So let's just, so now for now, A is a general Banach algebra, X is what I call a Banach A bimodule. That just means that X has module actions both from the left and the right by A, and they commute in the ways you would expect and so on, like in ring theory. And then the fact that it's a Banach bimodule just means that the module actions are continuous. And usually you expect that, say, A dot X is has no in norm is less than the norm of A times the norm of X, and so on. Okay. Then there is, once you have a Banach A bimodule, then there is a particular way to put a product on the direct sum of A and the bimodule, and that involves a certain bilinear map. So you start with a linear map S, okay? Then you associate with it a bilinear map that I call delta 1 of S, and it takes a pair of elements A and B and A, and what does it do? Well, it applies S to B, and then it uses the A module action by A on the left, okay? Then it subtracts S of the product AB, and then it adds, well, you apply S to A, and then you do the right module action by B, okay? So that's a formula. The reason for the form it has here is it comes from cohomology, and it's sort of the first one you have if you're trying to do these complexes in homology and so on, but on cohomology, but don't worry about that. We only need the first level here for what we're going to do. Okay, then the terminology is that S is a derivation if delta 1 of S is equal to 0. And if you know about derivations, I mean, derivations just mean sort of maps that satisfy the Leibniz rule. And of course, to say that this is 0 is exactly saying that S of a product is A dot S of B plus S of A dot B. So that tells you that S satisfies the Leibniz rule from differentiation. So that's why you have that terminology, that's the derivation. All right. And then the perhaps less intuitive notion, but which will be absolutely essential here, is that we call S an intertwining map if delta 1S is continuous. And the reason why that's absolutely essential is that there is a sort of, I guess this is standard from algebra, that if you look at the vector space A plus X, so just the Cartesian product of the two, in a vector space form, so the vector space operations are done coordinate-wise, then you can do kind of a twisted product on that one, not twisted in the sense that you're used to, but twisted by in the sort of colloquial sense that I sort of use my derivation here, my delta 1s. I use that to twist the product of if you like, the natural. I mean, the natural way to put a product on here is to just take the product on A in the natural way and then do the bimodule action on the other two, but then you can kind of twist it by delta 1 of S as well, and that actually will give you a nice associative product. And I believe, as I say, I'm sure this goes back to some ring theory and people, or algebra theory. People in algebra have done that for many years, I'm sure. But since we want to do Banach algebras, now we need the condition that S is intertwining. Remember, this means that this map here, delta 1S, is continuous, because that then ensures that this product here is continuous. And as I say, it's associative and distributive and whatnot. So then basically, if we put the L1 norm on the direct sum, then we get a Banach algebra with an equivalent norm. We may need an equivalent norm because this one may not be submultiplicative, the new product, meaning it's not always, I mean, there may be a constant involved, right? So normally for Banach algebra, you want that the norm of the product AB is less than or equal to the product of the norms of A and B. And in this case, it might just be there's a constant coming in. So you may need to renorm to an equivalent norm. It doesn't matter for our purposes. Everything is isomorphic, so that's fine. All right. And now the idea is that once you have this direct sum, and then we can just look at the projection of A plus X back onto A, and then we have an extension. All right. So that's my sort of basic extension, the one that is, I will call sigma here. So maybe I should write that up here. Let's see if I can maybe put that at the bottom. So sigma will now be the extension 0 kernel alpha into A. Sorry, not into A, but A plus X onto A onto 0. Okay, and maybe I should have given here a subscript S, because of course the product here depends crucially on the choice of my operator S, my linear map S. And it's very important, of course, that S is generally will be discontinuous here. Okay. So that was my short exact sequence. It is singular simply if you look at the definition of this map here and the fact that its kernel is essentially X, I mean the canonical copy in there of X. And if you look at how the formula was defined, well, when you have 0 in the component from A, then the product vanishes. So that's trivial. And as I say, I don't really care too much about that, but it comes for free, so I might as well say it. Okay, it is this one is admissible because it splits in the category of Banach spaces, because I can very easily write down a right inverse of my map alpha here. Simply I take A back to A comma 0. That's about a linear inverse, right inverse of A of alpha. Sorry. Okay. It also splits algebraically very easily, because if I take A to the point A comma minus SA, then you can check that that's a linear and multiplicative right inverse of this map alpha. Okay. So again, that's a totally straightforward calculation to do. That works. Okay. And well, then the question is, when does it split strongly? Well, I mean, obviously that has to do with, I mean, what could go wrong, right? If S was continuous, obviously this would be continuous, and then I had it. So I definitely must work with discontinuous linear maps S. But more generally, if you're willing to do a little bit of work, you can check that the my sequence up here splits strongly, precisely if I can take this map here and push it around a bit by a bounded operator, a bounded linear map from A into X, and then I get a derivation. Remember, a derivation was this thing that satisfies the Leibniz rule, or in other words, such a delta 1 applied to it is 0. Okay, so this somehow means I can perturb the product a little bit by this T and get it to be nice. Okay, so the idea now is, remember, I want to find a singular and admissible extension of little l2 that splits algebraically but not strongly. Okay, and so basically I want to use these conditions here. So I want to find a Banach A by module X, an intertwining map S. Intertwining is the one that ensures that I actually have a Banach algebra here. All right, and I want to ensure that S plus T is never a derivation, no matter what bounded linear map T I perturb S by. All right. And then I have a singular admissible extension of A, which splits algebraically but not strongly. So since I want to apply it in the case where A is little l2, okay, and I realize now that differs from how I did it here, because here A, this will be C, right? Okay, but since I want to apply it in the case where my quotient algebra here has trivial product, I'll now assume that I have trivial product. Okay, and also I will allow myself to assume that my right action of A on the bimodule X is trivial. I don't have any good reason for that other than it simplifies the problem and I can get away with it. So that's why I do it. Okay, so then of course my my rule for this delta 1s becomes very simple. Remember, originally there were 3 terms. There was A dot SB, then there was minus S of AB, but that has now vanished because A times B is 0, and then there was S of A dot B, but my right action is 0, so that's also vanished. So that's why I want to make those assumptions. Okay, because I say it's enough for my application. Okay, and then I check that under those conditions, well, S is a derivation by definition. That just means that delta 1 of S. So this map here is 0. And that's the same as saying that the image of S sits inside the annihilator of A in X. So simply the points in X which are annihilated by the right action. This is not terribly hard to see, right? If you look at this form here, right? If all of these here are annihilated by the action of anything, then you get 0 up there. Okay, so that's the role of the annihilator here. Remember, I absolutely need S to be intertwining. That's to ensure that this is actually a Banach algebra. Okay, and that was equivalent to saying that this map here is continuous. Okay, and then you look at the classical theory of automatic continuity, and there's something called the separating space, which is such a factor S. So the separating space of a linear operator S is simply the elements of the codomain of S, right? S maps into X, such that you can find a sequence in the domain which tends to 0, and the images of that sequence tend to X. And then you remember from your first course in functional analysis, the closed graph theorem, and this is saying that your operator S is continuous, is precisely the same as saying that the separating space is 0. Okay, so this is like a standard tool in automatic continuity theory. All right, and well, basically the idea is that for this guy to be continuous, I need that the separating space of S is contained in the annihilator of X. So then I use the fact again that if the separating space here is annihilated by this action, then that will ensure my map is continuous. That's somehow the idea. Okay, so the question is now, well, clearly this annihilator space is the key thing, right? So if I have a closed subspace of a Banach space X, when can I define a Banach left A module action on X, which will give me that as my annihilator? Well, it turns out that that's possible if I can find a bounded linear injection of the quotient space X mod I into the L infinity sum of countably many copies of Y. Okay, in fact, if let's see, if A here, the Banach algebra I want to do my module action by is separable, then this is actually equivalent. And of course, remember that I want to apply it in the case where A is equal to 2. So actually, this is exactly what I need. Okay, but of course, I mean, embedding even embedding Banach spaces into little L infinity is of course easy if they're separable, right? If you have a separable Banach space, you can embed it into L infinity. And so as long as y is non-zero, so I have a copy of little L infinity in here, and the quotient is separable, then this is fine, and this is what I need, okay? So let's summarize. We have A, our Banach algebra with trivial product. We have X, a Banach space, trivial right A module action. We have a linear map S, such that the quotient space X modulo this separating space, so the space that measures the discontinuity of S is separable, and then I can find a Banach left A module action on X, such that the annihilator of this associated with the action is exactly my separating space. Okay, and that will ensure by the previous result that my map S is intertwining. So I get a Banach algebra here in the middle, and therefore I get my singular extension that I want. Okay, and then I know that it splits strongly, precisely if I can perturb the operator S by some bounded operator T and obtain a derivation out of it. Or in other words, and well, that's the same as saying that I can perturb S by T, and then the image of A is contained in this separating subspace for S. So that requires a little bit of work to see, but this is not very hard. Okay, but now comes the bit that was hard, where we had to actually roll up the sleeves and do some work. Okay, and but this will also I think take me to the end nearly. So the key lemma here is you take any infinite dimensional Banach space, okay, and you assume that you know that any bounded linear map from it into little L1 is compact. Okay, think of A being little L2 if you like. Okay, and then you take a normalized Hamel basis gamma for A. Okay, so nothing about Schauder basis here. This is a vector space basis. Okay, and then you put X, your Banach space, equal to little L1 over that Hamel basis. Okay, so this is, I mean, if you take a Hamel basis for a Banach space, right, either it will be finite or it will be uncountable. So here, of course, I will only be interested in the uncountable case. So I'm now immediately into the non-separable setting. Okay, and then I can define a linear map S. Simply, I mean, I have a Hamel basis, so a vector space basis for A. So I define a map from A into some vector space simply by declaring what it does on each element of the basis, right? That's a linear map, and that's the way you define discontinuous linear maps, right? You have to do something along those lines, and this is exactly what I do. So I basically say the Hamel basis elements of A go onto the unit vector basis of little L1 here. So E sub A, that's just my notation for the unit vector basis in little L1 of gamma, okay? And then it turns out that that map will satisfy the negation of this condition, that is S plus T. So if I take this linear map and perturb it by any bounded map, then it won't go into the separating subspace of S, and the quotient, when I kill this separating space, I mean little L1 of gamma is a large non-separable space, but this separating space, I mean this map is so discontinuous, so bad that it has a very large separating space, and therefore the quotient turns out to be separable, and so we win. That was what we needed. Okay, so just putting the pieces together. Well, here's the result that Tomek, Richard, and I got, that the Banach algebra, little L2 tilde, has a singular admissible extension, which splits algebraically, but not strongly. And the idea is basically, well, we can forget about the identity, because we can just have to join identities at the end, the way I did earlier in the simpler case. So the idea is we pick a our normalized Hamel basis for little L2. Okay, we put X equal to little L1 over the Hamel basis, and then we take our linear map as before. Okay, and then we use Pitt's theorem to see that every bounded linear map from L2 into L1 is compact. So my key lemma applies. Well, since A is separable, the quotient x modulo the separating space S is separable. So X admits a Banach left A module action such that the annihilator space is just a separating space of S. Well, that was what I needed in order to ensure that S was intertwining. Remember, intertwining is the thing that means I actually have a Banach algebra product here in the middle, okay? And then my sequence is singular and admissible, and it splits algebraically. So all that's fine, but it doesn't split strongly because my key lemma, I showed that this condition star failed. I could not perturb S by a bounded linear map to get it to map into this separating subspace. And that's basically the end of the story. Okay, so the corollary is then, so this was basically getting my extension over here in this column. Okay, and now I just transport it over here where my B of ER of Reed's space is the quotient. So that I get the result I was after. Okay, so that's basically the end of it. Here are a couple of the key references. Thank you very much for your attention.
Comments or remarks? No? Just was silly observation. In that diagram of yours, the diagram, if 3 of the 4 sequences split, so does the other, which is the lemma that you...
Sure, yes, we just checked that by hand because we certainly weren't in the club of people who stare at diagrams at the time. And as I say, this is very underused in the theory of Banach algebras. So I'd like to see this applied more. In fact, this is the only case where I know that people have made any sort of, you might not consider this a serious use of it, but at least you have a useful purpose for things like pullbacks and so on. So yeah. And of course, this was also, I should say, it's not that I stopped doing mathematics in about 2017 or something, but I decided this would be a very appropriate topic to bring here, even though there weren't very many C of K spaces. But I felt when you go to Badajoz, you should have some diagrams and some homological constructions in it. So that was my motivation for taking it. Okay, but anyway, before we finish, I think we should all thank our organizing committee. So Jesus, Alberto, Nazareth and Ricardo. So thank you very much for all your hard work. I hope you will all join me in giving them a round of applause.
Okay, thanks a lot, but the organizing people have been Alberto and Nazareth and Ricardo and the rest, and Danny and the rest, we have been more or less. We have had mathematics, diagrams, lattices, yeah, more or less paraphrasing Leonard Cohen, we have fun and drama, almost like the blues. So please take a safe way back home. Thank you very much.